This is the fourth video lecture for chapter 4 and 4. This one is going to be about gravitational forces. In physics, there are three fundamental forces. Of those three, the one that we will really be concerned with the most is the gravitational force. The other forces, the strong nuclear force, we'll look at a little bit more in the spring. The electroweak force really is all electromagnetic forces, and it's recently combined with the weak nuclear force. This really goes to explain all of the normal things that we kind of consider as different forces: friction, tension, compression. All of these things are really just the interaction between different molecules and their electrons. By fundamental forces, we really mean that we don't fully understand how or why they work. We can come up with models for what will happen, but we can't really explain the why all the time. The really important thing here is just really to understand that we will be working with the gravitational force, which is explained further on. The gravitational force is an attractive force between two objects with mass. It is always an attractive force. The equation is as follows. The force due to gravity, or Fg, is equal to the gravitational constant times the mass of object 1 multiplied by the mass of object 2 divided by the distance squared between the two objects. R represents the distance between the center of masses between the two objects, not necessarily their surfaces. As I mentioned, the gravitational force is always an attractive force between two objects with mass. Here we have the moon with mass m, sub m, that's kind of weird to say, but m sub m, and the Earth with mass m sub e. You'll always see the Earth as always a capital M, or almost always a capital M, with a little subscript e. The forces are attractive. That means they are attracted towards each other. In this case, the force on the Earth is in the negative direction because it goes to the left. R is, as you notice here from this diagram, the distance between their centers of mass, which would be the center of each planet. Here, we're going to calculate what the weight of an object on the Earth's surface would be. We have the mass of the Earth, capital M sub E, of 5.89 times 10 to the 24th kilograms. G, which is the gravitational constant, of 6.67 times 10 to the negative 11th Newton meters squared per kilogram. And R, this is the distance from the center of the Earth to the surface of the Earth, or about the average of that, 6.38 times 10 to the 6th meters. This is also known as the radius for the Earth. If we look here in our formula to the right, we have the force due to gravity is equal to G times M sub E times M. That second M there refers to just some mass at the surface of the Earth. And we have R squared. So if we plug in our values here, and I want to make sure you go through and do this on your calculator, we should come up with some answer for these values here once we multiply them out that equal something that we're quite familiar with, or something very similar to what you've seen before. The force due to gravity, or some object's weight, is equal to the mass times the small gravitational constant of G, which you should be able to calculate the answer. Double check my math and make sure you come out with the right answer. Please check in with me when you get to class tomorrow. If you're having trouble with scientific notation, please make sure to come see me first thing in the morning before we get started in class. It's very important that you remember how to do scientific notation on your calculator, and as we move forward. Whenever the number in the exponent is raised, so 10 to the negative 11th, that means the decimal place is moved 11 spots to the left. Whenever it's positive, it's going to be moved 11 spots to the right. So in this case, 5.89 would be moved the decimal place would be moved 24 spots to the right. Here's one more practice problem. What is the weight, or force due to gravity, of a 760 kilogram satellite orbiting 320,000 meters above the Earth's surface? Here I give you the mass of the Earth, the gravitational constant. The radius is something that you need to figure out on your own. Take a moment, set this up, show your work, and go through it on your calculator. Below here, on the right in the diagram, I have a drawing that shows how the inverse square law works, because as the distance increases from the Earth's center, the force of gravity decreases. This is an exponential decay. Here, we have a diagram showing the mass of the moon and the mass of the Earth. Mass of the moon being m1, mass of the Earth being m2. We also have the force between the two of them, F. For each point here where it says A, B, C, D, and E, I want you to calculate what would happen to that force. How does that force change? So in the second situation, A, we have 2 times m1, and we still have the same m2. In the third situation, we have, for B, we have 1 time the same m1, and then we have twice the mass of the Earth. In situation C, both masses double. In D, the distance is now doubled. And in E, the distance is 1/2. So go through and tell me how the mass changes for each one of those situations. Please put this in your notebook. Bring this to class tomorrow. We will go over this at the beginning of class. Thank you very much. Have a good night and enjoy the reading.